In my talk, there will be many Russian important names, and I only fear that it will turn out that our result has been proven 20 years ago and published in some Russian journal. But let's see what happens. So welcome for the invitation. So our talk indeed fits in this long tradition held up in Moscow and other Russian names. So I will talk about quantified reflection calculus as a generalization of quantified provability logic. Now I have to see, can I go? Yeah, I can go with the pointers. Okay, so central notion in this talk is provability and formal provability and logics for provability to describe the structural behavior of provability. Provability, I don't need to defend it. It's a very important notion in mathematics, foundations of mathematics, logic, and meta-mathematics. And yeah, right, because as philosophers and as mathematicians, we wish to know the limits of proof, of what can be known, and therefore provability is this central notion. And as it happens, and as Gödel taught us, it can be formalized in mathematics. We can write a predicate. Can you see my hand?
Yes, yeah.
Yes, we can.
Okay, good, thanks. So indeed, we can formalize a predicate that's true on the standard model of the natural numbers, only exactly on the Gödel numbers of formulas that are indeed provable. So given, for example, a theory like piano arithmetic, we can write down, because in the end, the proofs are syntactic notions, so we can code it and write a predicate that exactly is reflecting provability. So it only holds on the Gödel numbers of provable sentences. Right, so this is, as we know, it's a sigma 1 notion, so it is of the form there is an object and this object is a proof. And as we know, it is essentially sigma 1, so finding such a proof is essentially non-decidable. And right, so Gödel used this notion, this is formalized provability predicate to give his famous results on his incompleteness theorems. And there were various structural properties, like, for example, if piano arithmetic can prove a formula, then piano arithmetic can introspect on this so that it sees that it will prove this formula. And this is important, that it holds for any formula A, right? Or any sentence in this sense. And well, using this, he could prove more, he could set this provability predicate to work, in particular after showing that we can do a decent amount of self-reference. And for example, if this famous liar sentence that says of itself that it's not provable, he could show that, okay, then actually if a sentence is equivalent to its own non-provability in this sense, then it will be equivalent to 0 equals 1. That is the consistency, or we can even write this as 0. If 0 equals 1 is provable, then 0 equals 1 is true, right? Which is just the negation of 0 equals 1 is provable. And thereby we can conclude, because of course lambda cannot be provable, because if it were provable, then since everything provable is true in piano arithmetic, because piano arithmetic is a sound theory, it must not be provable, and by this relation, indeed, it must not be provable, so it cannot be provable. Neither can a negation be provable, because if the negation were provable, then we get a negation of this fixed point, so then the negation would be not lambda, would be equivalent to provability of lambda. And then, since again using soundness here, I'm not being sparse on my assumptions, and you just use soundness because it's for this matter of position, then we get that also a contradiction. So lambda is neither provable nor disprovable, and that was the reasoning. I don't want to, I mean, you all know this argument. I just want to go over it, that in doing this argument, you use all these structural properties, and that gave rise to the quest of, let's find a list of all these provable properties, structural properties, right? Of course, stronger theories will prove this is called reflection. If Peano is proving something, then that something is true. And for that silliest something, namely 0 = 1, Peano arithmetic cannot prove that. If it would prove it, then it's true. Of course, CFC will prove reflection for Peano arithmetic. Okay, I would like to stress here that that this provability predicate is well known. This is sigma 1 complete, in the sense that any computably enumerable set can be written as the set of Gödel numbers for which are plugged into this formula. They are provable in arithmetic. This predicate is true on the natural number. So indeed, right, I use this as a sort of rhetorics to say, look, this is an inherently difficult predicate. However, as it turns out, we have already seen there are certain structural properties which can be proven about it. And as it turns out, we know the collection of all structural properties is actually nicely characterizable. As I mentioned here, Peano arithmetic will not even prove reflection for the easiest formulas well, one of the most easiest formulas that there is, namely something inherently false, right? This is Gödel's second incompleteness theorem. It will prove certain reflection, namely if 1 = 1 is provable, then 1 = 1 is true. Yeah, well done, Mr. Peano. 1 = 1. So of course, Peano arithmetic will prove reflection for this formula because it proves that 1 = 1. And as we all know, this is a general feature that if Peano arithmetic proves reflection, that can only be in virtue of the fact that this A is provably equivalent to 1 = 1. It's simple. It's a theorem of Peano arithmetic. And this, again, I want to stress, this holds for any formula A. And actually, this statement itself can be proven in a formalized setting, yielding to the famous Loeb formula, right? So these are interesting properties, useful properties that can be set to work if we want to apply this central notion of provability and apply theorems without digging into the details. And that's what a modal logic does. It provides us a set of lemmas, theorems, so that we can do our reasoning about this predicate in this abstract setting of a collection of lemma time theories. And that's the way I tend to think of modal logics, as a complete set of theorems. Just as we do when we do an integral, we don't do this Riemann sums and upper and lower approximations. No, we have a calculus for that, and likewise we have a calculus for provability in Peano arithmetic in the following precise sense. So we characterize all the provably structural properties in 2 steps. So we go to a modal logic consisting of propositional variables, a logical constant falsity, and taking boxes and Boolean combinations, right? So we have a modal logical signature, and we will denote it with L box. And then what we do is we think like these L box formulas, they really speak about arithmetic, but then for anything that this propositional variable can mean, right? So that is what we link the simple modal logic, propositional modal logic to arithmetic using arithmetical realizations, which is a function that takes a formula in our modal logic to a sentence in piano arithmetic, and propositional variables are sent to any arbitrary arithmetical sentences. Right? It connects with a Boolean connective, it commutes with the Boolean connectives, and we send the box in the modal language to this predicate. This predicate talks about numbers, right? That says provable in piano arithmetic. And from now on, I will cheat a little bit on notation, so I will leave out the Gödel numbering and numerals of Gödel numbering, etc. So that is for the sake of a clear presentation. Okay, and then we can say, like, this is a principle that we would expect to hold under any realization. This is regardless of the value of P and Q. We will have that if piano arithmetic proves it proves the antecedent, then by means of a formalized modus ponens or concatenation of proofs, I can make a proof of Q. This is regardless of this translation. And now, when this is in place, I'm sorry that I'm going so slowly, but I want to create this moment of miracle. I mean, so now we can define the provability logic of a theory, which is the set of modal formulae, such that it's always provable. So for any translation, we have that the theory will prove the translation. And yeah, okay, you know all this, but I really want to build it up like this, because actually it's a little miracle that this turns out to be a decidable logic, I think, right? We have here, this is a sigma 1 complete notion, like provability, and then we put a universal quantifier up front, and right, but you can code this in a number, because this any star really is only, I mean, it's only important what the propositional variables in phi will be mapped to. So this is also just a number. So here we have for all realizations, which is a code of a number, and then there is a proof. So this is pi 2 notion. However, we know that this is actually a decidable logic, and we all know the outcome. This is Gödel-Loeb's the logic, which has all classical tautologies in this language. So Q or not Q, but also substitutions instances like box P or not box P, etc. All distribution axioms, as we've seen before, and this formalized Loeb's theorem. And this together with the rules modus ponens and necessitation gives us the modal logic GL. And yeah, well, here's the miracle that indeed GL is sound and complete for this notion of provability and this interpretation. So yeah, I wanna stress that. So even though it looks prima facie pi 2, it is a simple decidable logic. Well, so it's p-space complete, but we call that simple. Right. And okay, what happened here? Yes. And we can play the same game with all true sentences. We have already seen that 0 equals 1 does not follow from the provability of 0 equals 1 over piano arithmetic. However, this sentence, of course, is true in the standard model. So we can ask for the true provability logic of a theory. So that's all the formulae in the modal language. Oh, something. So that for any realization, we have that n makes true on the standard model. So this is even looking worse, right? Because we refer to arithmetical truth and we put a universal quantifier up front. However, again, we have GLS, a simple modal logic describing this, the S for Solovay, and it's axiomatized by all the theorems of GL, and adding this reflection axioms to it, and modus ponens as only rule. Okay, so well-known theory. I'm brave to spend so much time on it with such an experienced audience, but I really wanted to recover this wow experience. Indeed, it is a little miracle that it's all decidable and nice, and not so for the quantified setting. So we can try to play the same game and ask for the provably structural behavior of the modal logic with now a quantifier. So what are we talking about? The language now consists of a logical constant, top or falsum, whatever, relation symbols, Boolean connectives, universal and existential quantifier, and the box. Okay. Now let's see. Define. We can link this again if we want this to describe a structural behavior of provability. We link this again to formulas of piano arithmetic by sending the box to formal provability. The for all maps to for all, Boolean connectives, but now the relation symbols will be just in interpretation. So it will be an arithmetical formula interpreting this relation symbol, right? And now the question is, can we do the same thing? So we can ask for the quantified provability logic of a theory, which is the model formally as before. Now the realization has slightly changed, but the definition is as before. For any realization, we have that T will prove the realization. And we have the true quantified provability logic, which says for any realization, we have that this realization holds on the standard model. And well, for a long time, it was believed that, well, this is what I've read. Later, you may comment what really happened. But the belief was held that adding simple principles like this one could yield an axiomatization of these two entities, quantities, right? Or logics. So for example, if for all x px is provable, then in particular for every x, that particular instance px will be provable. Well, it turned out to be much more different than this. Before I will give you the well-known results, let me just mention that that we cannot expect it to be decidable. This quantified right, the quantified provability logic. We cannot expect that to be decidable, because if we define the quantified logic of a theory to be just as the first order formally, and we do the same game, right? So we take that any realization, T must prove the realization of it. So we reinterpret all the things here in predicate logic, we reinterpret them here in arithmetic. It's important that we don't have equality here, but if we do that, so we take pure predicate calculus without equality, then we can play this game. Just ask for the quantified logic, so to say, predicate. And then it is not hard to see that actually the quantified logic of piano arithmetic must be a classical quantified calculus, right? So predicate calculus. And well, why is this? Well, there are two inclusions. So if I have a proof of phi in predicate logic, proof pi, then I can just take this proof and translate it under this particular translation to a proof of phi dot. Okay, And the other direction, let me see, how can I should be able to draw on it, right? On the slides.
Yes, so you leave the slides as they were, so you don't close the demonstration.
Okay, wait a second. Am I still sharing? No.
No,
Stop sharing.
Okay, I'm sharing again, and now I should be.
Yes.
No. You should make it full screen, and then you inside your yeah. So maybe you could do it. Yeah, you could do it here.
Ah, okay. Let me see.
The optimal way, I think, of doing it, because you need.
Yeah. I see. I have it. So it seems annotate, and now I will.
Yeah, but it's better to make it full screen now.
Okay, yeah. Okay, so I make it full screen now. No, first I have to select. Okay, so this is not easily working, so I'm going to appeal to your imagination. I will draw it without ink, so I will do it with a hand here. Okay, so the other direction. I should be able to do it. Wait. Annotate. Spotlight? No. Anyways, I will appeal to your imagination. So thinking construction in arithmetic, that's what we're going to do for the other direction. So suppose something is not provable in predicate calculus. So
but
then,
maybe make it full screen first.
Ah, it's not full screen?
No.
Is it now?
No.
Is it?
You just Control L in your.
Yeah, I did that. Can you see it full screen now?
No.
Then probably I'll just stop sharing my screen, and I will share it again. Okay. My apologies. Can you see my full screen now?
It's not full screen.
No.
Not?
But you never stopped sharing it.
Yeah, I did stop share it.
To make full screen, you need to make a full screen in your window that you are using, not in any.
I know. And
if it's Adobe Reader, you just press Control L or something like that.
Yeah. On an Apple, it will be Apple or Command L. Now it's full screen. Sharing is paused. Bring your shared window to the front. Okay. Do you see it now?
We see the old one. Maybe you should stop sharing and restart. So first go to full screen, then share.
Okay. That's a good suggestion. Okay. Can you see it now?
Yeah.
Yes.
Okay, good. Apologies. This would not have happened if Anna would have given the presentation.
By the way, you still have the possibility of writing on your slide from the Zoom menu, not from.
Yeah, I tried that, but that did not go as expected. So I mean, most of you know more about this topic than I do, so I will just use the hand and talk what.
Hand waving. Hand waving.
Exactly, literally hand waving. Okay. So for the other inclusion, by the way, I didn't stress that this is joint work with Anna Borges, which it is. It was on the slide, but I didn't say it at the beginning. Apologies. But so far nothing new appeared. So if something is non-provable in predicate calculus, that means, okay, it's not provable, so that we have this predicate, and we can write here not provable. So that consistency of this formula phi, not phi, right? So then we can just make a hanking language inside arithmetic, define that inside arithmetic, and define this Lindenbaum lemma, an infinite path going through the all possible extensions, and we make a maximal consistent set. And on the basis of such a maximal consistent set, and all these operations can be then defined in arithmetic, we can make a model. So you see here, it's actually more beautiful without pictures. You can imagine it yourself. You can, Sergey, you want to say something? Oh, no, okay. So you can imagine here appearing this model in arithmetic. You're defining the enhanced hanking language, and then you define your maximal consistent set by a path through all the possible extensions, and there must exist one infinite path leading to a maximal consistent set, and this maximal consistent set will give you an arithmetical definition of a model. You have to tweak a little bit with the quantifiers to have really for all x correspond to for all x, but that can be done. And then here you define an arithmetical model, which is a counter model to the non-provable formula. So indeed, if we have without the box, then this then quantified modal logic without modalities gives us, so to say, sigma 1 complete set, namely predicate logic. Now, so there's one case where we can compute another case where we can compute the provability logic, namely if we take the theory piano arithmetic plus piano arithmetic is inconsistent, because it really says there is no modalities, right? Everything trivializes, and that's where it ends. Okay. So now come the negative results. So I guess I first I mentioned Archimov's results that says that in the case of true quantified provability logic, it's hopeless. So this is not even arithmetical, right? You want to say something, Sergey?
That's right away. And waiting. The first non-trivial result was actually Franco Montagna's observation. Since he actually mentioned it as a standalone problem, whether a hypothesis, whether the quantified probability logic coincides with the quantified GL. It was disproved by Franco Montagna in 84, and by a very ingenious, as typical for Franco, extremely elegant construction, after which first I learned a lot about this, and all, if any, my achievements in this direction were actually derivatives from what I learned from Franco. And second, ideologically, it was absolutely clear that the whole area has negative, all other questions will have negative answers, because he really opened the can of worms with what kind of things you can interpret in. So the Franco is the name number one in this list.
Okay.
Thank you. Yeah.
Yeah, I am aware of it. So
just make it the part of your stamp speech. Yes. Good.
Thank you very much. Thank you very much. Yes, that I stand corrected. So Franco was the first to present a principle that is in this.
Yes.
But not provable.
Yes.
By the previous.
Absolutely. Yes.
And then we get that this set is as bad as it is. It is not arithmetical. And then by this beautiful story by Boulos, that he gets a Russian letter and goes by a dictionary and translates it. Yeah. And Vardanyan indeed proved the pi2 completeness of this set. And indeed,
yes, the preprint in Russian turned out to be much faster to organize than the publication in the Claudio of Academy of Sciences. I took the second path and Vardanyan took the first one.
Sorry, I didn't understand that.
Don't worry, don't bother. It's just everything is correct.
Okay, so and here we see that it's as bad as it can get, right? So for any we have a proof. So this is pi2, and indeed it's pi2 complete. And by a slight sharper version of Archimov's theorem, there was also pi1 complete in true arithmetic, that the true quantified provability logic of piano arithmetic. So that's the situation. That's pretty bad. Well, bad, or it's also nice that indeed it is such an intricate and difficult notion. Okay, so since you all know this genius proof much better than I just wanted to say that this beautiful picture that I made in your imagination of this model creation, which can be done, really boils down to this what is called Archimov's lemma, where we say, look, in modal logic, I can say, if the trick is played by taking the language of arithmetic as a particular case of predicate logic and embedding that back into arithmetic, and then using modal logic, where the box again stands for provability, we can say that every interpretation that is relevant is decidable, because if a number is 0, or a number represents 0, so z stands for 0, then it's provable that that number represents 0, and if it's not representing 0, it will be provable that it's representing 0. And likewise for triples representing the sum, the success pairs representing the graph of the successor, triples for addition, etc., etc. And then one could invoke this beautiful result of Tenenbaum's to say that any model of any model that is non-standard must have not non-recursive operations. So hereby we define, we enforce by this trick recursiveness, and therefore it's the standard model, and therefore we can embed just the standard model into this set. Okay. It turns out that these negative results are actually quite robust. So Vardanyan also proved that no model iterations and just one unary predicate symbol, then we have the same thing. It's also pi2 complete. And to me, I didn't check all the details, but it seems to me that this set, indeed, also, if I take the theory piano arithmetic plus incon piano arithmetic, that should also be pi2 complete. So really making it, just having one box falsum makes it trivial. Having two box falsum gives you pi2 completeness. And then Visser and de Jonge in 2006, when Lefbek Lemichel was still around in Utrecht, they proved that actually this is not a special feature of piano arithmetic. It holds for many theories, extending elementary arithmetics, being sigma 1 sounds. And they gave the title to their paper, No Escape from Vardanyan's Theorem. So, well, I'm a student of Albert Visser's, so it is my pleasure to now shortly submit a paper with the title, An Escape from Vardanyan's Theorem. And here is how Anna and I prepared this escape. So lately there has been many developments on strictly positive logics, and this is our escape route. So what do? We seriously restrict our language. So what will we work in? Well, we have relation symbols. Those will be so terms will be variables and constants, no functions. So it will, yeah. And we take conjunctions of those. Those are my atomic formulas. conjunctions of those, we have a logical constant for true. And then we take universal quantifications and only diamonds. And now we will go define a collection of sequence of the form phi implies psi, where phi and psi are of these restricted form. And the arithmetizations, what we do, we send propositional variables, relation symbols. We will send them to axiomatizations of theories. Right? So this is a tendency that is going on lately in reflection calculi. Now, of course, we have free variables, and the idea is that a unary predicate will be sent to a binary predicate, where one says I'm the Gödel number of a theory, and the other is a parametrization. So it will be many theories that will be parametrized by this translation of the unary parameter. Let's make this slightly more precise. Okay, but once we have given this, then we can hope to prove a soundness and completeness theorem for this carved out and restricted fragment. So that's what we're going to do. I'm going to explain it with more detail later on. So I want to say that our result pertains to three related current trends that we've seen in logic. The one is, I've put two names of here, the ones that I best know myself, so that's not entirely correct and fair, but Zachariashev and Walter and others, so that they use also strictly positive fragments, and they correspond to, they characterize the implicationaires of these form for these restricted A and B of some strictly positive forms. And something similar happened by reflection calculi, which gives rise to something similar, but a priori need not be like that. But the only thing that we do here in reflection calculi, we replace, it's a current trend that I want to place it in, is that we replace the realization of a propositional variable, instead of an arbitrary formula or an arbitrary sentence, apologies, we send it to an arbitrary theory, an axiomatization of a theory. And this gives rise to this beautiful work on reflection calculi, names of Beklemishev, Dashkov, hold on, right. So for example, and I want to embed this also in a third tendency, is that to look to this Japaritsa's polymodal versions of provability logic, where we add more and more provabilities. We do not yet pertain to this tradition because our paper only does one modality for the moment, but of course we will address more modalities later on. And right. And the nice thing is this reflection calculi, once we do this in the polymodal setting, we get results of this form again. And moreover, and this is a phenomenon that we see time and again, well, we don't know if P space is different from P time, but we do believe it is so. But we see that the decidability drops from P space if we only look to this fragment to P time. And this is a phenomenon that we see time and again. And it was this phenomenon that made us think that, well, maybe something happens with predicate provability logic, quantified provability logic. And this turned out indeed to be a good guess. So here goes. The calculus looks ridiculously simple. Don't disconnect now, because I will say something in defense of it. So true is provable. Phi proves phi. Here we see that we can sort of cut, right? Or right, we can compose proofs. Here we see that a conjunction proves a single version. And here we see what we need to write from, if if we can prove two formulas, then we can prove their conjunction. Then we have the simple modalities. This twice consistency implies the consistency, and here we see necessitation. Okay, and then the quantifier rules are as follows. So I can do a generalization in the expected way, and if I can prove psi from phi on t, then I can of course prove it if phi holds for any x. And then we have to add two more rules for the quantifiers. This is an important one. It says that if a constant really doesn't play any other role than being here, substituted for x, and we can prove a sequent, then we can prove the sequent outright for x's. So this sort of says the interchangeability of constants and variables if constants are not used otherwise than here. And this is important for our calculus. Okay. Right, so this is the system, and this is our escape. Now you may say, oh, this is equally simple as say piano arithmetic plus inconsistency of piano arithmetic, but I'd like to say something in favor of it. So first of all, we can make distinctions. So this formula will be provable, and this formula will not be provable, which is good, right? So there are distinctions to be made. And a derived rule is the following, that indeed, again, if C does not, if a constant can play the role of a quantifier, this is a derived rule. Now, it's not entirely silly, this enterprise, because I want you to recall that reflection calculus for omega is the same as what I've just presented without the quantifiers. And well, this allows for ordinal notations up to epsilon 0, and it caters a pi 0, 1 ordinal analysis. So it has applicability, it is non-trivial, and it can be worked with. And moreover, there are generalizations of this to RC lambda. When I write RC lambda, I mean that for any psi less than lambda, we have a modality, a diamond. Okay. So this just to say in favor of the calculus. It is an escape, and I think it is a non-trivial escape. Now let's get back how we link this to, hold on, I'm gonna check my time, 1 second. Okay, I have some 20 minutes, right?
In principle, you can finish at 8 o'clock, so you have time until 8, but leave some time for questions. So if you need more time, you can use it. But,
oh, you're talking 8 Russian
Moscow time. Yes.
40 minutes to full stop. So that's
okay. Okay, so let me continue. So how do we link this fragment to arithmetic? Well, as I told you, the variables we will use to flag the difference. We use variables x in the modal setting and y in the arithmetic settings, and ci will be mimicked by arithmetical variables zi. And then we take the true
relational, right? So it's terms are just variables or constants.
Yes, no functions. Yes, thank you for reminding that, Lev. So then the top will be sent to a standard axiomatization of Peano arithmetic. Look, it has one free variable to flag, okay, these are the Gödel numbers of axioms of Peano arithmetic, okay? Then if I have a predicate symbol with variables and constants, it will be mapped to an arbitrary sigma 1 formula that collects all the Gödel numbers, parameterized, the z's for the corresponding constants and the y's as parameters for the x in here. Very good. And I want all my, so this denotes now not a formula but a theory, and I want them all to extend beyond arithmetic. So I take the disjunction with the axiomatization of beyond arithmetic, right? So all the time you should read this like U is either an axiom of the interpretation of S or of beyond arithmetic. Now, if we take the conjunction of two formulas, that you must think of that like two theories together. So we take the union of the axiom sets. I see that, well, here it should have a variable U, I guess, to say we collect the axioms satisfying it.
The U lives, wait, the U lives outside the star, right?
Yes, yes, okay, very good, thanks. You're right. Indeed, now we're in the inductive case, so indeed we get the U back when we go inside. Very good, thank you very much, Anna. And here we have the diamond case, and the diamond will be mapped, expected, to the consistency. Okay, so now the consistency of the theory axiomatized by what is given in under the diamond. And consistency is just one sentence, and it says U is the Gödel number of this consistency statement, or U is an axiom of beyond arithmetic. And the for all, well, for all x, it says every number x, so it's this number and that number and that. So it's a big conjunction, and conjunctions were being mapped to disjunctions. So here we go to an sigma 1, so an existential quantifier. And note here that here we stay within the sigma 1 formula, and we use collection. So all theories that we work with will have collections to make things go smooth. Probably we can do a bit better, but let's not. It's not worth a pain. So yeah. So you see here we stay within computably enumerable axiomatizations. And now we take a sequent. So phi implies psi will mean that everything provable in psi is provable in phi, right? And remember, phi and psi denote theories that are actually parameterized by x. So then we say for all y, remember y corresponds to the arithmetical counterpart of x. So we say for all y, so we have everything provable here is provable here. So far so good. So this is complexity pi 2. Okay. Now, well, in this audience, I think I can not spend too much time on the arithmetical soundness. It is not hard to see that if something is provable in psi, then it's provable. Sorry, if phi proves psi is provable in our reflection calculus, then it is provable in beyond arithmetic under any arithmetical realization. Okay. I just want, you can look at this. This is just sigma 1 completeness, for example, this axiom, right? Nothing new under the sun. The only thing that I want to remark here is that we use sigma 1 collection again if I do a universal quantifier introduction. Right, because if I want to show that it's provable in this theory, then provable in this theory, right? Then remember, this is the union of all those parameterized theories. So if I want to use my inductive hypothesis, I do that for all the axioms that I have, and so I need to collect the proofs. They need not to be too big in my in the formal system. So that's why we need sigma 1 collection. But for the moment, we work over piano arithmetic, so nothing to worry about. And now I want to say some word on arithmetical completeness. And that's the other direction. So it turned out actually that we could just use Solovey's proof and separate the predicate part, right? Plug that in as a sort of a disjoint addition, and the proof could just be adopted. But the first step, of course, was to provide Kripke completeness for QRC1. And of course, if we want a nice axiomatization, it would be nice if we have the finite model property. And as we presented last year in Helsinki, indeed, we have the finite model property. However, if we want to embed the models into arithmetic, then we were fighting with it, and it turned out that things were much simpler if we have constant domains, right? And that is what we have accomplished now, and with that we could provide the arithmetical completeness. Okay, so let us give us a little bit of ideas how the relational semantics works. So what do we have? We have modal logic and we have predicate logic. So basically the modal logic we will have there. So we have our worlds that see each other, and each world now, instead of being a model for propositional logic, will be a model for predicate logic. Okay, so we have that each world itself is a model, first order model, but now we can do it with finite domain. And moreover, we have constant domain. And the relation will be transitive due to this diamond, diamond A implies diamond A. And well, constant will have the same denotation at every world. Okay. And of course, to evaluate the truth of in a Kripke model, we need an assignment that goes from variables to elements of the domain. Okay, I think that is all as expected. And how do we then define truth? Well, if I have of my formulas, we define it, of course, by induction. And the atomic case, if I have an atomic formula, here, for example, I have a binary formula. When will this be true on my model in a world W? Well, if of course under this assignment, remember the assignment takes my terms to elements of W, then it is an element of the denotation. Okay, this is from classical predicate calculus. And the diamond we of course do as before. We say when is diamond phi true at world W if I can see a world V where phi holds. And the for all x is as usual. So I leave everything as is and change x to anything that's of my liking, and then it still must hold. Okay. So far so good. So this is the expected notion of truth in my Kripke models. And it's very easy to prove that if phi proves psi by an induction on the proof, we have that if at a world in any world, in any model, under any assignment, if phi holds in that world under that assignment, then psi holds as well. Okay, good semantics, but there was not much to be expected. Even I put another thing in here to say something in defense that the logic is not entirely silly. For example, you can require that the domains may be as large as needed. So there for example, we have a formula that says all S holds on all possible combinations of X, Y, and Z. Now let's try to refute this. And here it says that S holds on all possible combinations, the first two things the same, and then this different, and now here and here, another combination of that, right? So if I want to refute this, so without modalities, then you can see I need at least 3 elements, right? Because if I have 2, then they must be because of this. Then S must hold on all of them, because pairwise they must be equal. And this can be extended to any arity. So the thing that I wish to say is the models are not entirely super trivial. The elements, maybe there's no a priori bound on the elements. Okay. Now we have relational completeness. So that if phi does not prove psi, then there is a finite model and an assignment such that phi is true, but psi is not true here. And we have the finite model property. That means a finite number of worlds. And moreover, every world has a finite constant domain. And that discusses the decidability of our quantified reflection calculus. Just a little bit of ideas of the proof, but it goes. Yes.
So you have this completeness with respect to constant domains, constant domain semantics, and so this agrees. So this presumably shows that analogs of Barkhan formula are not expressible in this strictly positive language, right? So that's basically the.
Well, we have. Let me go back here. We have them in a sense, right? So this is as close as Barkhan as we can get. So we do have this implication. We do not have this implication. And this is the closest we can get in the signature.
Yeah, so Barkhan formula would, so how do you, so it's box for all implies, yeah, it is for all box implies box for all, right? So that's Barkhan formula. For all box implies box for all. And here you have diamond and for all, so that's not quite, so that's not Barkhan, so to say.
No, this is as close as we can get.
Mm-hmm.
Yes. Actually, we thought at first that because of this, we thought that we needed.
Provable in pure quantified K or something like this, right? So this one.
Well, yes, and we thought that because of this this property, we would need at least non-decreasing, but actually we thought we would need to add more and more witnesses as we grow, and this would then tell us that the domain cannot decrease. That's right, but actually the witnesses in a higher world have very little to do with witnesses in a lower world. So unless you have a constant to denote them, there can be anything. So if the start of your domain is large enough, then you have enough freedom to do whatever you please, and therefore you can take constant domain. So I tend to think of it as a sort of finite overflow, so to say. It's not a lack of expressibility. Take your number of constants large enough, and then your language cannot discern from growing and growing domains and the top, which is this big number of constants. We will see this reflected in the proof shortly. Okay. Okay, so we were in the relational completeness. We're gonna build a counter model, and we use standard techniques. So we're gonna use a term model. Of course, our language is now so restrictive that we cannot keep track of negative information. So the trick that we employ is our worlds will be parts of two parts. So all formulas are positive, but one is saying positive information about negative states of affairs, so to say. So these are formulas in our strictly positive fragment that say things should not hold at this world, and these are formulas that should be true in a world. And then, of course, what we start out with is with a set of formulas consisting of just singleton phi and singleton psi. And the idea is we're going to make this to a maximal set in a sense, so that all this will be true in the model and all this will be false. Okay. And that is what we call well-formed pairs. Some standard notation. So delta is provable from gamma if it follows from the conjunction in our setting. And this probability is, of course, QRC1 provability. Closed if we have only constants in there. Consistent so that something that is provable from the positive part will not occur in the negative part. And it's maximal if every formula in some, some adequate set of formulas, yeah, right? Because if we want to make a counter model for phi implies psi, then we're only interested in phi and psi and subformulas. So that determines some adequate set of lambda, and we call it maximal if either the formula is in P plus or in P minus. And it must be witnessed, right? Because we're doing predicate logic. So if there exists X formula, we don't have exist, so it means for all X phi is in the negative part, then that must be witnessed in the negative part by substituting a term for phi, for X in phi. Okay, so this is as to be expected, and then we say a pair P is lambda well formed if it is closed, lambda maximal, consistent, and fully witnessed, as to be expected. Now, what we do, the thing is, of course, there's a little problem because we need to close off on the formulas. If for all X is in the positive part, then we need to add many substitutions in there. So can we always find a witness, a free witness, an available witness? And so the thing is, yes, we can. And the trick is as follows. We put everything in a negative part, except the things that are strictly forced to be in the positive part. And if the starting number of constants is large enough, then this works. So if the number of constants that we work with is exceeding twice the maximal number of constants in formulas in lambda. So the maximal constant count in lambda means, so I take any formula in lambda and count the number of constants in there. And then I need to take care of the universal quantifiers, because every time I eliminate a universal quantifier, I introduce a new constant. And moreover, I do that in phi and in psi. So that's the number 2. And if I make sure that the number of starting constants is larger than this, then whatever I do to peel off my universal quantifiers, I will always have a fresh constant to witness a negative formula. Okay, so this works. I'm not going to go into the details. And then we can make step by step a counter model. So we start with a psi non-provable from phi, and then we build this well-formed world W extending phi psi, and we choose C large enough, as we've seen in the previous slide. This is the so to say the overflow that the model language cannot see that the domain is constant or growing or whatever. There's enough. Okay. And in the end, of course, the denotation will of a relation symbol at W correspond to the membership in this set. And that is the model that we end up with. However, we do this for one, so we get one well-formed pair or well-formed world for this non-provable sequence. And then, of course, we must build the model with more and more future worlds. So what we do is we repeat this process. So every time I have a diamond chi in the positive part, that means I must find a witness where chi holds. Well, then I repeat the moves. I take I take the pair starting singleton chi, and then I take all the deltas and diamond deltas, because I need a transitive model in the negative parts of the world I had before. It must be well founded, so I add a new delta for diamond formula in a negative part, and I can apply my lemma again, get again a well-formed pair, etc., etc., and I'm gonna glue these together, and in this way we construct our model. And this works. Okay. So putting it together, so we can then prove a truth lemma, as we always do. So we say that if I build this model of this construction as I just described, semantic validity at a world under evaluation is the same as saying the valuation applied to this formula is part of W plus, right? Remember, this is a pair of true and false sentences. Right, and thereby we have our relational completeness. So if phi does not prove psi, then we can find a model where phi is true and psi is not true in a certain world under a certain assignment. Fair enough. Now the arithmetical completeness proof, and it's extremely simple now if you know Solovey's proof, because what we do is we say, so phi is not proves psi. Now we're going to embed this into arithmetic. So we take our rooted tree that we found, where we call the root world 1. We put a world 0 under it, where our Solovey function starts, and then we embed all the points. So disregarding the relational extra first order structure that it has, we're gonna just copy shamelessly the proof of Solovey's completeness result and construct these lambda formulas, these sentences that so for those who don't know it, in a sense, they mimic the behavior of the tree. So we make this model M, which is a tree. We put one world under it, and then every world in my tree will correspond to a lambda I, and the lambda I mimic the structure of the tree in the sense that each lambda I will correspond to the tree. The only worlds that are the lambda i's. If you are one world, you're not another world. That's what this formula says. If you are the world, then you can see then the consistency. Consistency is you can see, right? You can see the future world. So each lambda I will prove the consistency of the lambda j's that are accessible from I. And likewise, if lambda I is true, and all these properties are provable in T, then provided I is not 0, it's provable that one of the succeeding visible worlds, accessible worlds, is holds. Okay, and of course, this is this famous Solovey function. You will never leave the Solovey function that starts at 0, so lambda 0 is actually true. Now we go to the arithmetical completeness. So once we have this embedding of Solovey's, it was just very simple. We could separate the modal behavior and the predicate behavior, and that was just a little gift. It turned out to be not too hard. So what do we do to prove this? So suppose something is not provable in QRC, a sequence, such a sequence not provable. Now we take our counter model, we embed it into arithmetic, and then what we do is we take the interpretation of a predicate to be as follows. So basically, if you forget about this part, it's just Solovey, right? You say, here I have a propositional letter. Where is my propositional letter interpreted? Well, there where the propositional letter is true. Now it's not a propositional letter, so we take disjunction over all lambda I, where this is true, right? Because we say, now we require lambda I, and now we say, look, I must be equal to some of the things in the extension of my predicate at world I. Of course, if it has an empty extension, then this will be the empty disjunction and will be false, and therefore this lambda I will be discarded. So of course we get only these lambda i's where S has a non-empty, non-trivial extension will play a role. But the nice thing is that we can separate the relational part of the proof with the lambda i's, and we just juxtapose it with the predicate calculus proof. We take really what we say is, remember that the free variable xk will be interpreted as a variable yk, right? Yeah, but yk is a natural number, so they're infinitely natural numbers, and we have only finite domains, right? So therefore, what we do is to really talk about arithmetic. We take modulo the number yk modulo the size of the model, so that you go cycle over all the elements of your model. Okay, and this really does the trick. So if you take this interpretation, it's pretty straightforward that if chi is provable in I, then this interpretation of chi follows from lambda I provably in T. And yeah, this is typically one states the two items. This of course follows from this, but to get the induction going, you stated both for the formula and the negation. Okay, so that's good. And then the proof goes as always. So phi does not prove psi, so we have a world where phi holds and psi does not hold. So by the truth lemma, phi, the interpretation of phi for this particular assignment will follow from lambda 1. Not psi will also follow from lambda 1. And remember, not psi is not in our language, right? But in arithmetic, it makes perfect sense. It's not in the signature, but in arithmetic, it makes perfect sense. And lambda 0 is true. Lambda 0 implies the consistency of lambda 1 because 0 can see 1. And then by this truth lemma under the books, we get that lambda 0 proves the consistency of this. And since lambda 0 is true, we get that the negation of this, that this formula is true, which is just not provable this, and we are done. So right, because remember, this really says that for all theta this should hold. So in particular, this settles the matter. Okay, here's some more reasoning that I will skip for now. So I want to close off the presentation. So we have an escape, and the thing is that I think we can extend it to hiding arithmetic because the soundness works for hiding arithmetic, and these are pi2 statements, right? These interpretations. And we know that piano arithmetic is pi2 conservative over HA. And moreover, this is provably so. And moreover, the complexity of the unprovable substitutions using Solvay is sigma 2. By the way, I want to make one remark that actually in the proof that we've given, the arithmetical soundness, we don't use infinite axiomatizability. So we just use finite extensions, and that's why we could link it to the regular Solvay proof, because really our arithmetizations are different, our realizations, right? They're theories, but we realize that we can do it with finite extensions of piano arithmetic. So then we can use all the techniques from Solvay again. So as a corollary, we get that quantified reflection calculus is also the quantified reflection logic, strictly positive quantified provability logic of Heyting arithmetic. Quantified and it works also for the for the version without quantification. It's a simple observation, but I want to bring to your attention that the provability logic of Heyting arithmetic is still an open problem. So I think it is nice that we have, I mean, modest, but we have a little progress here. Okay, to sum up, well, there is no recursively enumerated quantified provability logic with this. However, in QRC, we go to the quantified strictly positive provability logic. We have it. It's decidable. It's sound and complete with relational semantics, constant domain. It's sound and complete with arithmetics. Actually, the proof that we do can be, you can scale it down to, say, elementary arithmetic plus sigma 1 collection, or say I sigma 1, and it seems to work perfectly fine for Heyting arithmetic. And well, now some nice questions that we can think of. Can we relate it to really a fragment of quantified provability logic? So we've carved out. I think we can, but we need to check some details here. Do we have the same for the? Do we also have a nice characterization of the always set of true sentences for quantified reflection calculus? Because notice that we now have a drop from pi2 complete to decidable, which is nice. I mean, we had a drop by going to a strictly positive fragment from p space to p time, and now we go from pi2 and we go all the way down to decidable. I think we can talk it into p time, but that needs attention. We need to look at that. So we need to gauge the computational complexity of QRC1, study a bit the properties, interpolation, etc., maybe other semantics. And of course, we want to go to the polymodal version of it. And just as a curious question, I pose this one. Is this set also pi2 complete if we take some slow provability notion, right? We know that for box falsum it is, for box falsum it's not. Well, what about in between? There are nice, I can mention Archimov's recent result on this, notions of slow provability. So one can think about this. I would be very curious to hear the outcome. Can we enhance the expressibility of QRC1 without losing decidability? And of course, I think that if we have done this step to more modalities, the polymodal version, then actually some arguments in our Pi01 ordinal analysis project can receive a more uniform treatment, because certain arguments apply to this, but also to this. And if you take the general structure of it, you have a sort of universal, a predicate calculus version of it, and then that may simplify proofs in this field. So that is, I think, all I wanted to say. Thank you very much.
Thank you very much. Okay. Are there any remarks or questions to the speaker? Tadeusz, please.
Yeah, the first remark is the same, I think, that I have after Anna's talk in Barcelona. So I think that this notation of L subscript box for all is still confusing, right? I missed the first part of the lecture, but this is a language which includes implication as well. The difference that does not lie here in the presence of box versus diamond. And therefore, the question that I posed after Anna's talk is still on. I don't know if it was mentioned, but it still makes sense to ask what happens if you actually add box or replace diamond via box in your calculus.
I stand corrected. My apologies. Yes, you're right. It should, and even the diamond is not. So we should flag it with like a SP or something like this. Maybe L super SP lower diamond, strictly positive. Yes.
Okay. And another comment was purely bibliographic one. So you mentioned Volter and Zahariashvili in the context of this SP. I guess that the paper that you have in mind is the one they wrote with Stanislav Kikot, with Agi Kuruc and Tanaka. And actually, these are the first authors. So they come at the end. So if somebody is looking just for Volter and Zahariashvili, it wouldn't be so easy to find. But there were, of course, quite a few earlier references. I think the one which is particularly worth mentioning, which was like 20 years earlier, was the Celani and Jansana work, where they did quite a bit of basic theory on Goldblatt-Thomason, on several basic results for this strictly positive fragment.
I didn't know this work, so I think they had positive rather than strictly positive. So that is with disjunction and box.
Give me, yes. Sorry, I didn't think about disjunction. Yes, actually, I think you may be right. I think that they would actually have disjunction.
Yeah, so so there is a separate strain of papers, in particular by Jansana and Celani, I think, and some others. So where on positive fragments.
Yeah, they would have box and they would have disjunction. Indeed, yes, it's the lack of implication negation only.
As computationally simple as the strictly positive, however, who knows? Maybe in terms of in this context of quantified probability logic, maybe they also allow to a larger escape, so to say, from Vardanyan theorem.
Nice, good suggestion.
Whether this is true. I guess my conjecture would be rather not, because in particular you can express the real Barkan, so to say, not the fake Barkan by Joost and Anna,
But do you expect any problems with disjunction, Joost? So, or do you expect combining both disjunction and box? Would that already lead you into dangerous area, or still you may still escape?
That would be my intuition, but I don't really know. So that's could be anything to have an answer. So seems to be a very interesting problem.
It's a very good question. So at least you stay in CE axiomatization, so that's fine. So you can properly make sense of this in this project.
So in terms of interpretations, everything will be all right for this.
Yes, but for the model, it's a very good question, and we must most definitely look into it. Yes.
Please, yes.
Thank you. Yeah.
At least it's also not obvious how to do the Tenenbaum trick, so to say, in this restricted fragment, in positive. So with disjunction and box. Maybe it's possible, but we don't know. Sergei Nikolaevich, please.
Reflection calculus itself has a very significant foundational implications. It may be regarded as a contribution to the quest for the refined ordinal notations. It has new true unprovable properties in arithmetic. Nice normal forms, any kind of promise, potential in this direction from the quantified version of it.
You mean promise in terms of applications?
Well, applications,
or
applications at least to the same areas. What does it yield any new approach to ordinal notations? Let me ask it in a simple form.
I haven't thought about it, but I mean, it does allow for a lot more uniformity. So I can imagine that, for example, you can now perform arguments where you quantify over interpretations, where interpretations, for example, yield over arbitrary fundamental sequences.
Yes.
So that may give us a way of not fixing a particular fundamental sequence. So that may give us some room of improvement, but this is entirely unexplored.
So this that's an interesting question, because I have been thinking about it all the time while Joost was giving his talk, so to say. There might be some potential there, I think, because this quantified calculus is about, as it is clear, about parameterized families of theories, and where you consider unions of such. So universal quantifier corresponds to the union of a parameterized family of theories, something like that. So you can extend your theory to the. So in that language, you can sort of, in a restricted way, but still deal with such things, and that may be useful for example, even in the ordinary, in the usual applications, we sort of dealt with infinite families of formulas. For example, when we formulated reduction property, it was kind of natural, for example, for us to have some, would be natural to have in the language something like infinite conjunction or something like this. So here we have this universal quantifier that may actually express such things. But
it is not clear, but it's promising. I mean, it is not, at least. I cannot say that the answer is negative. So I have hopes that indeed something can be done. Yes.
And also, I want to add some inspirational remark. In one of the recent talks, Barbara Porti, the famous linguist, whom many of the people present know, who is famous for moving the center of American linguistics from MIT at Stanford and Stanford to University of Massachusetts, where he resided for quite a while. She said, don't be afraid or don't be discouraged if you don't find your area, the area of your interest. It may not exist yet. It means that in your case, the quantification injection can raise some issues which people in ordinal notations don't think about. They haven't thought about it. So be open for really new contribution to maybe a small one, but still it's a new dimension, and they didn't in which they didn't. I don't think they actually thought about. Okay.
Thanks.
Also, this quantified strictly positive logic may even have some applications outside probability logic or this exploration or reflection calculus. So, in general, if you deal with quantified strictly positive calculi, let's say in the problem, maybe they are also related to problems in description logic and such things. So you can enhance the formalism of description logic by this kind of quantified. So you are still in the decidable domain, which is good. So maybe that's will be also helpful in some way.
Ah, that's nice. Yes. Anna, do you share my my hopes of talking it into P time?
Possibly. I didn't spend a lot of time thinking about it. But yeah. It should be possible to just build a counter model,
Yeah.
like in a way very similar to how it's done for RC.
I also have a question partly to Sergei Nikolaevich. So, do you remember that paper with Japaridze?
I hesitated to ask this because I'm asking too many questions, but thank you, Lev. Yes.
So there was essentially the arithmetical completeness by embedding of finite models for which you obtain finite model property. So this was a language with a single variable, so all predicates were de facto unary. Do you remember how the models looked like? So this was kind of hybrid of S5 and GL, right? So they were also like predicate GL models with finite domains, but were these domains constant or were they not constant?
No, they were not constants, but the finite domains, it was the only constraint. But you know, finite countermodels, and there might be some connections.
What is this paper, Lev?
So that's a paper by two authors, Archimov and Japaridze.
Journal of Symbolic Logic, late 80s, maybe the early 1990s. I'll send it to you. Just
thank you. Please do.
There's a completeness and decidability of this the fragment of probability logic in which with the finite domain, with the finite countermodels. So basically, the main lemma is that any finite model can be embedded, Solvay style. And
what is the? Do you get pi2 completeness as well there?
No. That's the other way around. It was a positive result.
Okay, good.
It was a positive result as well as yours. So that's.
Okay. Yes. Well, actually, Anna and I have been working with this completeness proof, and there's a lot of room of scaling that up. So what I think, Anna, we have had something similar, right? An observation that any embeddable through constant domain formula can be, so we use constant domain. I think we have now a trick where we can avoid constant domains, but at some point we had a similar conjecture. So that you see that it always happens that when you prove something, then 20 years earlier there's some rush.
But also 20 years in the future, because there's a group in Japan which are now digging out all this finite model stories in the Kurahashi.
Kurahashi, yes, I'm very well aware. I'm very impressed by their research.
Yes, absolutely, and I think that you have to know each other, at least to be communicating with each other and sharing what you have.
We are, yes.
Very good. Thank you, Lev. Yes.
Okay.
Can I also ask or suggest something about the strictly positive stuff and connection with this Tanaka and Kikot and Kuroc and Zaryachev work? There is actually Satleti here, which they spend a lot of time on, if I remember, namely, and this may have connection with this question that you are still not completely sure about whether phi entails psi in your calculus is the same as phi implies psi being valid when you actually have implication. So they note that Kripke completeness can go wrong in different ways when you restrict the signature, right? So there are cases where
when you restrict that.
When you restrict the signature, when you throw away actual implication, right? So there are cases of things which are trivially valid over set-based semantics, where you don't restrict your attention just to upsets of posets. So similar to what you have, right? So you are using ordinary semantics in a sense. There is no restriction on upsets. If I do upsets, and there is no partial order built into all this, if I understand correctly. So this is natural semantics for signature without implication, without Boolean negation. But there are cases then of things which are in this where you actually get additional incompleteness result in that that you have some kind of disentailments that should be provable, but are not in this restricted signature without disjunction and without implication. So actually, this is not all plain sailing, and it is interesting whether you can avoid this kind of traps and issues. From this point of view, your creepy completeness result is interesting, I think.
Yeah, no, we definitely need to study this paper, at least know all the authors of it.
It starts with Kikot, but Tanaka was also very much involved. It was one of his few occasions to return to actual modal logic research. I knew him quite well. He was a PhD student of Hirokirano when I was doing my PhD there, but then later he had to do a different job, and then he got an opportunity to visit Frank Walter in Liverpool, and then he did all this research. But this is a very huge group of 5 authors at least, right? So there is Kikot, there is Agikuruch, and there is Tanaka, and then of course Walter and Zaryashchev as pillars. So even if you look at this long list of papers by Walter and Zaryashchev, you can tell it apart by having particularly many co-authors.
Yeah, I can comment on this in the following way. So indeed, the main topic of that paper is that indeed the completeness problem for strictly positive logic. So not all strictly positive normal logics are complete, and sometimes they do not correspond to any. They are not fragments of any specific usual normal model logics. So that's there are many examples, but they study the general question, find some criteria, and show that this is not decidable actually for a strictly positive finitely axiomatizable calculus to determine whether it's a fragment of a model logic or not. So that's an interesting, definitely and technically difficult result. However, I would like to remark that in our business of probability, strictly positive probability logic and reflection calculi, there are examples of both. So, of course, the standard reflection calculus fragment of GLP is indeed Kripke complete finite model property and very nice, so to say. But once you go upwards and add a modality which corresponds to the full uniform reflection principle, and that's exactly the case where you go also from finite extensions. You have to consider infinite extensions of infinitely axiomatized extensions of your theory, and then you obtain a system which is also decidable and polytime, but not cryptically complete. So it's not doesn't correspond to a class of frames.
So which reference is this? Where is it proved?
It's proved in my paper in 2014 in the volume dedicated to the birthday of Sergei Artyomov. So it's the first case where we consider modality which is not in the range of standard model probability logics. So there it is studied. But there are other examples of arithmetically meaningful modalities which are not strictly positive modalities, which are not complete in this sense, do not correspond to standard model logics. So that's the phenomenon which is somehow occurs. So that's the situation. Mm-hmm. Okay, if there are no more questions, maybe we will. So I would like to congratulate Anna and Joost with a nice paper. So that's definitely an interesting result. Okay, thank you very much.